So we're going to start out our discussion today with a review of another interesting program that demonstrates some parallel streams features. And this program is available here in my GitLab Live Lessons Folders Parallel Streams project. So you can clone that and take a look at that and follow along. So we're now in the IDE for the parallel stream example. And you can see here there's a bunch of files. Let's go ahead and take a look at the main file. And this example shows how to use various Java parallel streams features and sequential streams features, for that matter, to count the number of files in a very large recursive folder hierarchy, as well as also calculate the cumulative sizes of all the files. And if you want to see the sizes of all these things, or the actual things we're dealing with, here's the resources folder, which has quite a large number of files. You'll see exactly how many files and how many bytes here shortly. And this is basically most of the source code that I use for the examples. So it's just a very large copy of all the source code. So let's go ahead and take a look at the program. The main program starts out by warming up the thread pool so we get more accurate results. And then we go ahead and we run a bunch of tests. And you'll see that the tests are designed to either use parallel or sequential streams. And so we start out here by essentially running things with sequential streams. We pass in false as the parameter for parallel. And then we run the tests again, except this time we pass in true. And the tests go off and run with parallel streams. All the tests are timed, and we'll see the results at the end. This takes a little while to run, so let me go ahead and start the process running in the background. And we'll come back and take a look at the results here in just a minute. So let's go ahead and take a look at the various tests. For example, here's one that uses either sequential or parallel streams and the Java ternary operator to do all the processing. And it works by creating an instance of this file count stream class, passing in the root URI of the works, which is this large recursive file hierarchy, the flag that says to do parallel streams or not, and it will call this run test method, and run test is just going to time the time it takes to compute the results, and it stores it in a hash table, and then when we're done, we'll print the results out, and we'll sort them so you can see which tests worked fastest and which tests worked slowest. And then we're also going to go ahead and print out some statistics relating to the number of documents, the number of folders, and then the ultimate size in megabytes of all the contents in this recursive hierarchy. So that's kind of the driver program we use for all the examples. And so we have one that does the file counter stream implementation. We have one that does this thing called file count stream indexing, which uses this cool direct indexing technique we'll talk about. And then the last example we're going to do here is kind of fun because it uses something called the Java teeing collector. And this is really just to show this teeing collector. You'll see that it doesn't necessarily make it run a whole lot faster, but it's kind of fun to see how it works. So let's go ahead and take a look at the solution. So we'll start with the simplest one. This is the file count stream implementation, which uses the Java streams framework and the Java ternary operator, which you may recall is the question mark colon operator, to compute the size in bytes of a given file hierarchy as well as the folders reachable from this initial file. The constructor just stashes away whether we're doing this in parallel or not. And then the key method here that does all the work is called compute. And so let's go ahead and see what compute does. First thing compute does is it takes the parameter that was passed in, that's actually stashed away in this thing called an abstract file counter. We'll take a look at that in a second. The abstract file counter is the superclass for all the different classes. And it basically just keeps track of state that's needed to implement the various subclasses. So we keep track of the file that's being analyzed. We keep track of whether we're running in parallel. We keep track of the number of documents we've seen so far. We keep track of the number of folders we've seen so far. All those fields are static because we only need to have one copy of that for all the different recursive path traversals we're doing. And then it has an abstract method called compute and a couple of helper methods. And then it's got some interesting methods we'll come and look at in a second that do the processing for documents and also do the processing for folders. And we'll look at that when we get to the right part of the main file count stream computation method. So here's the compute method for a file count stream. You can see it takes the file that we have as the root at this level, which initially starts out to be the root of the entire recursive directory structure. And it goes ahead and gets a list of files. Now, this is not a list. It's an array that contains the files that are at that particular level in the hierarchy. And we turn that into a list, so we have a list of these things. And then we use this little trick I like to use a lot when I'm trying to do tests that either do parallel or sequential streams. We check to see if the parameter is, Boolean parameter is true or not. If it's true, if S parallel is true, we use a parallel stream factory method to turn the list into a parallel stream. If it's false, we use the stream method, which makes a sequential stream. In either case, once we've got a stream, either sequential or parallel, we then use the map to long intermediate operation and the ternary operator. So what we do is we say, for each file, is this file a file? Now that seems a little strange, but that's the way it's called in Java. So it's either going to be true, in which case we've got a document, or it's false, in which case we have a folder. So if this dynamic check is true, we go ahead and handle the document, and that simply increments the document count by 1 and returns the number of bytes in the document. And if it's false, if we've got a folder, not a document, we call handle folder. And handle folder, as you can see, is going to take the folder and a function, and the function we're passing in here is just basically the constructor reference for file stream count. And so handling a folder means we go ahead and increment the count of folders by 1, and then we take the function that was passed in, we apply it, so that'll make us a new object of the appropriate subclass, which in this case is file count stream. And then we call the compute method on this to count the number of bytes in the file rooted at that subfolder. And we do this, we factor this stuff out so we can reuse the same handle folder method for all the different subclasses of abstract file counter. So this will end up returning a stream of long values that indicate the number of bytes at each of the different documents or folders, subfolders. And then the last thing we do is we sum the sizes of all the files. And that's what gets returned from compute. Notice that compute will be called recursively if we encounter folders along the way, because we are going to call compute for the subfolder that we built with that function. So that's the ternary operator version of this stuff. Let's go take a look at the indexing version. This has very much the same design, but it does something a little bit more clever. What it does is in the field portion of the file count stream indexing class, it goes ahead and it makes a 2-element array of 2 long function objects that are parameterized by file. And 2 long function is basically a specialization of the function functional interface that is customized for long types. And what we do is we have the 0th item, the first element, the 0 at location 0 in this particular 2-element array, be a function that is going to go ahead, or actually it's a lambda expression, that's going to go ahead and call the handle folder method, passing in the folder and passing in the function that creates a new file count stream indexing object. So that's what's going to go in here. And then in the location, that's location 1, which is the second location in the 2-element array, we're going to call the handle document function. So this is a lambda expression that we'll call handle document. So the 0th location handles folders, and the first location, which is really the second location, the one at index 1, handles documents. Now we're going to see how we actually use this in our compute method. So if you recall, for file count stream, we use the ternary operator to decide whether we're dealing with a file, document, or a folder. In this case, we do something a little bit more clever. As before, we create a list of the files at that level. We then convert that list into either a parallel or sequential stream. And then we use map to long, except this time, rather than using the ternary operator, we're going to compute the index into the mops array. So recall again, mops is an array of 2 lambda expressions. And the way we're going to decide which of those 2 to choose is we're going to use a very cool helper method defined on the Boolean class called compare. And compare takes 2 Boolean values, and if they're equal, it returns 0. If they're not equal, it's going to return 1. So in this particular case, if the type of entry we've got here is indeed a file, then that's going to return true. And when we compare that with the value false, that's going to return a, if it is a file, then it's going to return 1. Otherwise, if it's not a file, if it's a folder as opposed to a document, that is, then it's going to return 0. So documents will get the value 0, will get the value 1 from this comparison, whereas folders will get the value 0. And that's why the folder is handled up here in the 0th location, and the document is handled here in the 1st location, the 1 location. So this is going to basically directly index into that array, get the lambda expression stored there, and apply it as a long passing in the entry. And so we can do direct indexing rather than having to use the ternary operator. In any case, we sum the results, and that ends up being the sum at that particular level in our recursive hierarchy. So that's kind of a neat technique. The third and final approach is going to use something that's called the teeing collector. And we'll show you what the teeing collector does, and we'll also explain what this particular set of fields do. There's one called mDocument collector and mFolder collector, and you'll see what they do in a second. So here is the implementation of file count stream teeing that uses the teeing collector. The first part's the same as always. We make ourselves a list of the files. We convert that list into either a parallel or sequential stream. And then we skip the map to long phase altogether, and instead we use collect. And collect is going to use the teeing collector. And this is interesting because there's actually 3 collectors, actually 4 collectors, but 3 different combinations of collectors being used here. So collect is being used with the teeing collector. And the teeing collector is this interesting collector that was added to Java 12, and it takes 3 parameters. It takes 2 parameters that themselves are collectors, and then it takes a 3rd parameter, which is basically a binary operator that takes the results of the 2 collectors and combines them. So at a high level, what we're doing here is we're figuring out the number of bytes that are documents and the number of bytes that are folders, and then we're summing those 2 things together. So that's the big picture view. Now let's kind of zero down on each of these different collectors that are kind of sub-collectors. So this is called filtering. Filtering is also a collector that was added to Java. And what filtering does is it goes ahead and it runs this predicate. In this particular case, it's saying, if we have files in our stream or documents, then use this downstream collector called mDocument collector to compute the sum of the bytes in the file. If we have something that's not a file, in other words, if we have a folder, then we're going to use a downstream collector that's going to collect things that are folders. And I'll show you both of those collectors in a second. So isFile and not isFile are basically predicates that are used to filter the stream elements that are coming through the teeing collector. So let's go ahead and take a look at the mDocument collector, which is a downstream collector. And here's what it does. It uses the collector of factory method, which takes, in this case, 4 lambda expressions. The first one is the supplier, and that's going to be the type that's worked on by this collector, which is going to be a new array that has a single element in it. And we need to do this because of the semantics of lambda expressions where you can't make direct changes, so we have to go indirect through a 1-element array of longs. The accumulator then takes that 1-element array value, so like location 0 in that 1-element array, and it calls the handleDocument method. Remember, we saw handleDocument before, and that's the one that increments the document count and returns the length of the document. So that's going to go ahead and increment this running sum of the bytes. And then the combiner, which is called when we're doing a parallel stream in order to combine the results together, when you have 2 elements that have to be, 2 subresults that need to be combined, that's going to take 1 long array with 1 element and another long array with 1 element, and it's going to add the 2 values together, and then it's going to go ahead and return that result. So we've updated this result, and we return that result, which is that 1-element array. And then the final lambda expression here is a finisher, which takes the array, the 1-element array, and returns the value of the 1-element array, which is the sum of all these various computations. So that's what the document collector does. That's a downstream collector that's called in order to be able to collect the results that are filtered to be files. Let's go take a look at the folder collector. Similar idea, just slightly different implementation. Once again, it creates a one-element array as the supplier, which is what's stored as the mutable result container within this collector that we're creating with the collector of factory method. We then go ahead and have the accumulator take the running sum and increment it by calling the handle folder method, which, as you see, creates the appropriate type of object and calls compute recursively. In this case, we're going to pass in the file count stream teeing constructor reference. The combiner works exactly what we saw before. The finisher works exactly what we saw before as well. So basically what's happening here is we're running these downstream collectors on the appropriate types of entries in the stream, and then the teeing collector is taking those results and then applying this binary operator, which is going to sum them up. All right, so now that you've seen how the program is designed, let's go ahead and take a look at the results. Now, the interesting thing is if we run these a couple times, you'll get slightly different results. Usually the file counter stream, which is the one that uses the ternary operator, and the file counter stream index, which is what uses the direct indexing, they run at about the same performance in parallel. And you can see that they're both somewhat faster than the file counter stream teeing method. It just doesn't give us quite as much of a bang for our buck. It's a little bit higher overhead, probably because the collectors need to have some additional work to tee them together. And then we see that the sequential versions also run slower, not wildly slower, but a bit slower. And you can see that the sequential one that uses indexing is the fastest. The sequential one that uses the ternary operator is slightly slower. And the sequential one that uses the teeing approach is slightly slower than that. So basically, that's a walkthrough of this example. Hopefully that gives you some ideas of how to use different optimization techniques in order to be able to improve the performance of the different mechanisms available for use with streams, including things like that direct indexing approach, the ternary operator approach, and then more advanced approach, the teeing approach. The teeing approach is actually really not there for performance reasons. It's there for other reasons, like wanting to be able to combine the results of two other computations.